Hello guys, this is Carf Coder back with another video, and today I'll be starting a new series called as GPT from scratch in C++. So I'll be using my own library. This is my own library, TensorLib. This is basically a NumPy type of stuff, but I'm trying to make it. It has everything that NumPy can do, almost everything. But I'm trying to make it into PyTorch so that it works well and stuff like that, right? And well, today our agenda will be to make the attention mechanism, the single head attention mechanism from scratch in C++ on this library. So we'll be making softmax and the single head attention layer, self-attention layer actually. So well, that will be our first video. The next video will be about multi-head attention layer and embedding layer. If I can actually do it in one video, or else it will be directly about embedding layer. After that, it will be about joining them to, and all of these videos will be verified against PyTorch just to make sure there is no error in it, right? Now, after all that works, I hope you know how normally how the transformers are made. So I hope you know the basic idea of the transformer architecture. Go and check out 3 blue 1 brown videos of deep learning if you don't know. Great guy, teaches it very well with visual input, so you can actually check it and see it, and it's very interesting to see it. And yeah, you can also check out make GPT from zero. So voted playlist, actually it helps a lot if you want to check it out. You can like copy the architecture if you want, right? And he will be doing it in PyTorch, but I will be doing it in C++. It's just extra work and more time taken, but it will teach you a lot about machine learning rather than just importing PyTorch, right? So we will be making a GPT from scratch in C++, and the GPT will be trained on some domain. So you'll be making it a small GPT, right? For the first time, we'll be making small GPT, and it will be trained on around 1 million tokens, I think. So it can be trained in like 30 minutes or so, and I will be trying to make the code be single threaded. Multi-head attention will require, I think, multi-threading, so I have to check it out. So yeah, except that every code will be single threaded, right? I will first do that, make a GPT, train it on something, right? And then actually ask questions and see if it works or not. If it works actually, then provide it a small bit of UI, just to, HTML UI, just to check it out if it works correctly or not, right? And then I'll do add optimizations after that, like SIMD, multi-threading, and if possible, some tilde too. So that will be a roadmap. So I think it will be done in like 5 to 6 videos, where there will be an embedding attention mechanism video like this one, embedding layer video, multi attention mechanism, so multi-head attention mechanism. So that will be third video. Then the MLP, the forward feed network, how it actually works, and then an embedding layer, which basically gives the GPT the answer, like tells it how what word to generate after actually going through the process, and then it will be all be trained through Autograd, which I will be making the system. Autograd, I don't think I'll make a separate video for it. If you guys want, I can make a video for it, but I don't think I'll be making a video between because it will take a lot of time, and it's just basic mathematics, I think, comparatively, like you would say, it's just basic mathematics, and I have to just add API calls, right? Except that everything is going to be working like that, right? And yeah, so just to give a small brief coverage on my TensorLib library, it's kind of like NumPy. It has the TensorRNG. Okay, so it has CSVlib for data pipeline and stuff like that, so it can pass data, pass CSVs. it has two tensor to convert it into my tensor type, right? The tensor implicit shape, strides, data buffer. It contains the shape, strides, and data. So basically, um, in my library, the tensor is basically a 1D array, but represented in form of multi of a matrix. So first of all, I just need you guys, all guys, to know that you can represent a 2D, 3D, or ND array in form of a 1D array. That is done through tensors. That's what my library basically does, right? Tensor RNG is for setting the seeds, like set 32 seed and stuff like that. TensorOps just gives us atmol and transpose, which you actually need for this, and some basic operations. After that, I think we have Autograd / node, graph scaffolding. So the Autograd part is currently like not done at all. Like it has some basic implications, I think. Actually, I think there are some parts which are done, but yeah, okay. So the class has been made and stuff like that, but it's not done completely. So check, be out ready for that. So I think I may make a video if you guys want, but I think I will do that film. It depends upon how much time to take, right? So yeah, it uses C++23, and yeah, that's all about it. If you want to build it, you can build it like this. Easy to build, not that big of a deal. Now, yeah, that's about it. Okay. Anyways, what I was saying is, for this, I have like skeleton open, and I will use some things. If it's like kind of doesn't look that good, it's because I made it with AI just to make it quickly. I didn't want to write everything in here, but yeah, it looks well, I guess. So no problem. This is softmax example. Softmax, if you don't know, it takes an input. Input is a container which contains some numbers. It shifts it. Shifted part is basically done to make it come into a range, because e to the power 1000 is a very big number. We don't want that. So we bring it to a stable range. Then we add exponential to every part of it, sum it, and then divide it by the exponential. We get a probability distribution, and it all adds up to one, right? It preserves the relative importance. People ask, like, it's probably asked why sigmoid is not used. Well, sigmoid is not used because it gives independent classification results. So it has independent importance, not relative importance. So that's the main thing. And then these are the points we next want to see. And so I will actually add an image of it, right? This is the workflow of how it works. I'm not going to actually go through everything. This is all high level. If you want to check it out, can. This is the D model, is basically the embedding model. dk for a single head will be equal to D model. So if D model is 8, then dk is also 8. So don't worry about that. Again, check out 3 Blue 1 Brown, check his videos, and then it will be very easy for you to understand. So the matrix multiplication is basically okay. So let me just clarify. These are all randomized, right? These are all random weights. It's better to initialize with Xavier formula. And input X is basically the embedding. So the sequence is into D model. So let's say the sequence length is 3. If I love pizza, so there are 3 words, so it will be sequence will be 3, right? Just remember that. Once we check that, we can just see X into WQ, X into WK, X into WV provides a sequence into DV, DK, which is in the sense and implementation to show that, okay, if the embedding is this like this, then the attention weight should be something like this. Then the formula is used. Formula is K into Q into KT divided by root over of dk, scaling it. Then casual masking is applied, right? You can just check this out. Is it how it works, right? Casual mask, we will be not applying that right now. just for the simple purpose of it, right? Prevents the attention to future tokens, right? If you're using or making BERT architecture with it, which is basically GPT, but there are some differences in little bit of difference in the architecture. But if you're making that, don't use casual mask. If you're making GPT type stuff, then we use casual mask. Then we use softmax to bring it into probabilities. 10 multiplied with V to get the value vectors, and then that's the attention of it. This is the attention weight. So basically this is the attention weights, right? And then into V, you got the attention of. So I'm making this in the code, right? What I will be doing simple, will be very simple. So I just made a file in this single attention that just add it in here. So okay, just add single add condition. Here and then this thing, right? I don't really need a thing in that, but I would need TensorLib, so let me just do that part. I'll be showing and giving a brief instruction of how my library works while I'm doing this, so there will be no problem, right? First of all, we need tensor package. This provides us the tensor architecture for it, right? Let me just add okay. So first of all, we need to I'm going to assume the sequence length and the model, the embedding model that we're going to use. For now, let me just say, okay, you know what? I will, okay, let me just say HTML XPR is size T, size T, and it's size T. Then let me say the sequence length equals 4, right? Then I can just do the same thing. Let me just say that the model in the model equals 8. So 8. Okay. So check it out. That's what I'm doing. D model into dk, you know, that will be weight WQ. So as I said, dk is equal to d model, okay, in single head attention. Single attention, these are equal. So I can simply just say p dk equals, that's the key basically in the sense you could say that 8. I can just say okay. Once we're done with this stuff, then we can actually make the thing that I want. So we're going to use tensor. So our type will always be tensor. When we're making an actual matrix for it, right? We can initialize it with WQ, and as I said, this is random. So for WQ, let me just say WQ, right? Equals our tensor, right? Tensor 8 random tensor. See this? This is how we do in this thing. So we provided a shape. Now the shape can be anything, but I can say it is our sequence, our D model, and dk, right? And then I say that the initialization type is 0. Simple as that. This is great to use, okay? And yeah, we do the same thing for these two. And basically this dv is basically dk in this case. It's single head attention. I didn't want to make it too complex for it, but it's basically in the most easiest sense dk. Okay, so we just copy this, I guess. Let's copy this and then paste, finish. Paste 4 times. Okay, that's the query, and this is the key tensor. Key tensor will have the same thing. This is our value tensor, and then this is our embedding model tensor. So embedding model will have a different thing. It will have, as I said, it will have sequence length into order. So you can do it anyway. Great. So this is how we are going to initialize everything, right? W2, W3, WV. Now that we have random weights in it, using this here, we have to simply just do multiplication of it with x to get the actual q. So for that, we have to do matrix multiplication. And as I said, I have these already. So for that, I have to include another thing, which I include TensorLib, and then I can call it Tensor. So now we just say cups, right? And then it can be then I can see maximal. That means simply as that it comes in here because it's simply right. So the matrix multiplication to produce q will be used right now. So we just call it tensor and then q, right? So matrix multiplication of x and wq. So x and w will give us q. Simple as that. It's that easy. Okay. After that, we can simply just say tensor of k or e will be using. Anyways, what I was saying is then the q becomes our TensorLibs, right? Matrix multiplication of x and w. Simple as that. Right after that, to tensor of v equals TensorLibs, right? Matrix multiplication of x and w. Simple as that. Now these are done, right? We get k, q, v. Now we can actually use the formula in here. So now we will actually require softmax ahead of that. So we're going to also make softmax for it, right? So once you're going to when you're going to make softmax, you actually need to make it in the tensor format. So leaving that for now, let me just create this and this, okay. So what I can simply do right now is transpose it. So let me just say tensor. Oh, you know what I can do this. Actually, I can say transpose will equals TensorLibs, right? That's one definition. But we do so q and transpose to be of our transpose 2D of our k. Okay. Query and keys, we get the which part of it and stuff like that, which matters, like when the query is something, what will be the key and stuff like that, and just that. Now we can scale it. So for scaling it, we have to let this go root of t. So the tensors scale scores will be our can either do two things or three things, but I think what will be better is using tensors. Or you know, something that this usually uses is I can get the data pointers for it and I can change it inside of it. So that's great to use in stuff like that. Right? So what I'm just going to do is make a flow just so you can see the type of how it actually works. Auto, let me just name it scores will be called on scores into the data pointer is for pointer, so we can see that. Now for size t I is 0 and is less than our stores want to put the size when I plus plus do that is to understand the problem in that. And remember, we are using tensors, so it doesn't really matter. I don't have to do it in O(n) squared time loop, right? I can simply just store it in this format and I don't really have to worry about traversing it again and again, right? It's the total thing that will impress you. So scores equals scores will equal to 5, right? So scores multiple point of I, and then I can simply just say one of the I just here, then I can simply just 2 root square root. So now it's looking just times below random square root, and I simply just pass in the one argument so for scores I just put this in and so yeah, different process. You have to make wait second. Oh, sorry, my bad. Okay, I'm stupid. Yeah, sorry. What I was trying to say is that it works like this way. Yeah, sorry, my bad. I forgot that it is the same thing but with the data pointer, right? So it does the same thing. It's a float pointer. I forgot. So my bad. Okay, so we get these goes into a pointer and then do this like that. So what we get is basically these scaled scores, you could say, right? Now I have to apply softmax to it. So it should be something like final scores would be equal to softmax of the scores to something. It should be something like this. Okay. And I can call it scale. I think it is better. Yeah, that's just better. Okay. So intervals represent distance that and that is most database. So to implement softmax, I have to do ops, right? So here I actually add it. So I had the fragment into pages, so I think I just need to do them tensor while doing this, and we should take the softmax, and we should take a tensor that. Now current blocks that means these we just see that we can use family blog, which I think can be and so softmax like good stuff, right? Okay. So now I have to just use the formula of this thing. So the formula is basically consider maximum. Maximum is easy to get. You just do ranges maximum right, and pass it the initial values just t. But if you have to look at it, okay, it doesn't work like that. That's why I have another way to call it. So we can just t dot values. So we get the t max. Now we want to minus it with everything, right? And while minusing it, we need to exponent it. So minus it, exponent it, the minus ones, and then sum it, right? So what I want to actually do, and it should be row wise. So the main thing is that it should be row wise. It shouldn't be the whole tensor, right? It should be only row wise. So it is for zero. Without the chain, zero position, of course, and then plus plus, right? For the chain, zero plus time, without the chain, one, right? Then plus plus, we have that. We're going to simply just go through it and actually do all this stuff to it, right? And actually add each piece on. Let's flow. This. Great. Conventional and conventional now, if we actually check it out, we have to shift it. Shifting is easy, right? We have to actually add another thing in it, just called the data pointer, which is the table. So output and the control will be mutable. So we come to the control. Before that, I've also create an output tensor. So tensor output equals tensor read singles, use, and then my tensor plus 20 sheet, right? Let's pass the sheet. And yeah, okay, it goes the shape, and then we can give if we do a pointer, then it is basically output dot the pointer, right? And yeah, float it. So now I can simply just say the output Mutable pointer for some reason isn't showing me. Okay, the pointer will be waiting for the position 5 into down. Tries from here. That's okay, and that's what we do. This is try T impedance in the touch files. So I impedance now T 0 plus J into T 1 should be equal to this should be equal to the shifted value, so the value in that, right? So to get data values, we data followed. I'm just going to this. Okay. P dot data pointer and yeah, it should be equal to T data pointer with the same thing that happens in Tensor T 0 plus 2 into slide T 1, right? Minus, so the data content is minus T max. Not that to happen, right? For that, we simply just do exponential of it. So standard exponential of it, so I think it shifted and changes it. What is it? I can simply just add our standard it's okay. What do you mean comparison? Oh, my bad. Actually, sorry. My bad. So we just do that, right? And then we get something like that. Then we sum it, and then we actually figure this. Okay, so it's being sum should equal to output pointer, and we just do this. Now just this in here. Right. Okay. Simple as that. Okay. Now, since I'm using it, I can actually check it out and then from the softmax level. So the softmax will be like this, pointer will put all of these in. So that's turn row sum in turn normalization, so divided by the sum again and again. And then it has okay. So we do this, and then after that I can simply just say we do this to normalize it, normalization is just another this interpretation is the sum, so now we can just do output then I can just do this thing. Just here equals our normalize this and this. So just output movement at this point, right? This point divided by this sum, and that's about it. So this is what it does is finds the SP, right? Exponential. Then we sum it. And I think we want to sum this together. So now okay, so this is multiplying, this is added. So once this is added, we need to this thing. We have to normalize it. That means by this, by this means with this. But then here, if you check it out, yes, this sum is not completely so to get into use for this. Not looking for it. Continue for it. Last this is just into this little change this in this place. Yeah, that's it. After that, we will get it and then we will simply just turn output. Is it that so? Let's see this. Simply just see. Also, if you're wondering, I forgot to talk about it. If you're wondering, if you're wondering why I did this minus, right? There's a formula that's called that helps in this. So basically, mean it's a mathematical formula, but means softmax. The softmax of x is equal to softmax of x minus c. With different with c is max of x. Simple as that. If it follows this is what is doing basically, so it works, right? Okay, so now I can simply just say that, okay, in mind we have something called which is softmax. Right? And the softmax will take in the source scale and then give you the scores. And I'm going to show you the tensors and that, right? Sorry, our scores. So our scores takes it and makes final scores, right? And then we get the attention weights. So the attention weight will multiply with V. So now we can simply just call it tensors. It is output equals place into V. So final scores we need null. Final scores. This is the basic stuff that we can do, and then attention output is that. So let me just add one thing that my language is called TensorLib. That allows you to that allows it to make a certain seed for it and keep it equal, right? So now if you go in the chart, right? Okay, put a name, single attention, what kind of single attention, single attention, single attention. Okay, let me just see if it works. What's the problem now? Oh, yeah, I'm really blind nowadays. Okay. So now I can see the Ninja and then to make it, some problems. Okay. I forgot I have this. And for that, so we can just remove this part from the line. Okay, once it works, it should work correctly, and I should have output tensors in the form of this divide. No, 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 actually works, you see this for this type of so much time is genuinely pleasing. It is genuinely pleasing of how much time of family takes to do this. And I'm going to come back when this is done. Okay, so that's finally done. And well, actually, now I actually added this function right over here, save CSV. It just saves the CSV so you can verify it with PyTorch, and I will just add it right over here. I wanted to have what I had don't actually just make sure it's okay. We just and I also wrote the Python code, so it will take these and then actually test it out and stuff like that. So I just call save CSV and then I'll just add W Q and then to the file name as let me just call it CSV just to store it in here and then just W to CSV and yeah, okay. Okay, that's way better. Now, actually, let me just wait in here. Social if file system just if not a source is then we have to make like it. Then file system okay, that should be nice. So we have to paste this footer and want to just coordinate A V Now let's just bring it again just to see what's happening. Now apps in yeah. Okay, so it gives me these also, right? Wait, important single attention by that. I think this exists from somehow made that credible. Doesn't think together. It's interesting. So I can simply what to say. I'll be one. Output field. I'll simply just no, I simply just it. Yeah, just do that. So I just paste and see on upgrade demand actually. I'm using this. And I'm going to paste something. Okay, so now if we check it out, for some reason not working. I don't know. Okay, so single attention head, single attention head. Okay, sorry, because it's like that, it should be for plugin program. Now there should be excuse me also know that is doing it. So now I can actually pass it over here. We can just equals continuing system. So now I can check yes, yes, and then as well as so now let me just I could also do here, so this is a problem. So slash then activate you'll be done in the UI. And yeah, if you actually check it out, it's almost the same. Children. Almost the same. It can be just check it out, it's almost the same. Everything matches almost. Right? Yeah. So this is our single attention head and it perfectly works now. I verified again. PyTorch, it works correctly. This is the images. I may share it in that, or I will check it out how to share it without any problem. I may share it and keep it as a switching in that so everybody can check it out, right? And well, yeah, that's about it. It's 48 minutes, so it's a bit of a long video, but yeah, and that's how these things work in the most easiest sense, right? And that's about it. You can check it out. This is a single head inference done. I will add more videos about multiple head, embedding layer, MLP, Autograd, and finally the GPT architecture totally with embedding and training nothing model. So yeah, that's about it. Thank you for watching. And if you guys have any suggestions, leave it down below. I'll post this code into our I'll put this code into GitHub and yeah, I'll check it from there. Okay. Thank you guys for watching. Like, subscribe if you liked it. See you guys later.